question number 3 says, a 5-meter length of steel with a cross-sectional area of 20 centimeters squared is compressed with a force of 20,000 newtons. If the Young's modulus of steel is 200 times 10 to the 9th newtons per meter squared, what is the change in length of the steel beam? So the first thing I want to do here is write what I want to find. And it's the change in length. And we're also going to write all of our knowns. So we have an original length of 5 meters, a cross-sectional area, A equals 20 centimeters squared, and a force of 20,000 newtons. So anytime you see a question like this, you also see that it has the Young's modulus constant for steel, which is Y equals 200 times 10 to the 9th newtons per meter squared. So the first thing I think of when I do this type of question is, okay, we have the Y for Young's modulus. Let's go back to stress and strain. So we know that stress is equal to force over area, and strain is equal to change in length over the original length. Well, we can relate stress and strain together by using Young's modulus. So to make stress and strain equal each other, we have force over area equals Young's modulus times the change in length over the original length. Now, if you see a question that says the bulk's modulus or the shear modulus, these are almost the same exact as these Young's modulus questions. Instead of change in length, you would have a change in volume over the original volume, and you would have a constant of B. But since they're all similar, we're going to go ahead and plug everything into our equation. So it tells us, remember, you always have your force in newtons. So if it would have gave us a mass that we were using, we would have multiplied it by gravity to get our weight force in newtons. Now the tricky part of these questions is the area. In this question it says the area is equal to 20 centimeters squared. Well, you have to remember for a wire or anything that the area is equal to the cross-sectional area, which is pi r squared. Here, Dr. Sullivan was nice enough to give you the area, except he gives you the original length in meters, which is 5 meters, and this is in centimeters squared, so they have to be both in the same units. So we have to convert to meters squared. So to convert 20 centimeters squared to meters squared, we do 20 centimeters squared times 1 over 100 squared. And that gives us an area of 0.002 meters squared, or 2 times 10 to the minus 3 square meters. So let's go ahead and plug that in for our cross-sectional area. Now we can go ahead and plug Y in, which is Young's modulus, in for Y. So 200 times 10 to the 9th newtons per meter squared. And then the change in length is what we're looking for. And we know the original length, so we're going to go ahead and plug 5 meters in for here. And now we have everything we need to solve for the change in length. So we do 20,000 divided by 0.002 divided by 200 times 10 to the 9th and multiply by 5, and we get an answer of 2.5 times 10 to the minus 4 meters. And looking at our choices, everything is in either millimeters or centimeters. So we know 2.5 times 10 to the minus 4 meters is equivalent to 0.25 millimeters if we multiply 2.5 times 10 to the minus 4 by 1,000. So your thought process when you're going through a Young's modulus or a Bulk's modulus question is, first look, maybe he's just asking you for the stress and he's giving you everything extra like Young's modulus and the original length. Well, if he just asked for the stress of the object, all you do is do the force divided by the area. If he's just asking for the strain, you just do the change in length over the original length. And if he's asking to solve for any of the variables, just go ahead and plug everything in for the force, the cross-sectional area, the Young's modulus, or Bulk's modulus if this is a volume, and solve for your change in length when you have an original length of 5 meters. So the correct answer for question number 3 is A, 0.25 millimeters.